I'll be giving a presentation today on pinging a nuclear meltdown, inherent weaknesses in ICS SCADA, and how do we secure it. Do a little introduction. I'm not sure it's live. There we go. Awesome. Okay. And that is probably the least embarrassing photo I could find. So my name is Byrnside. I've come to this venue as a captain in the South Carolina Army National Guard. I am the Computer Network Defense Team South Lead, so I'm responsible for computer network defense for state infrastructure and Guard resources. I believe we're looking from Columbia to the coastline, so I get the beaches, which is great. For my day job, I'm an associate at Booz Allen Hamilton. As you can see here, both of various experience, some more revealing stuff at the bottom, of course. Got the slew of usual information security certificates, CSP, GCI, CDA, GCSA, Security Plus, Net Plus, Scrum Master, and I'll be taking my GWAP, GIC Web Application Pen Tester within the next month or so. So that's a little bit of my background. And I come to you in the capacity of the ICS SCADA expertise based on the experience I have supporting the National Guard. The South Carolina Army National Guard is looking to become an incident response capability for the state in the event of a potential intrusion into critical infrastructure within the state. Bearing in mind that we have more than 5 nuclear facilities in the state, power grid infrastructure, all of our water resources. This is a pretty big deal, so we've been getting a considerable amount of training on this capability and working with various government agencies, a couple of 3-lettered ones, and of course the U.S. CERT with the Department of Homeland Security. So great relationship building and great knowledge to be gained. So without further ado, we'll go ahead and jump into it. So what are control systems? When we talk about control systems, we're talking about specifically industrial control systems. These are the systems that control all the infrastructure that you see in the state, and really any other automation process that takes place. This is basically the factories that make car tires, Twinkies, all those automation processes are generally controlled by industrial control systems. It doesn't necessarily have to be SCADA. We're going to deep dive into SCADA because that's one of the bigger ones. But distributed control systems, process control systems, and energy management systems. Some of these are a little bit more specialized, but as they mature, they also tend to blend together. So a big group name that we call them is ICS SCADA. So essentially, and the revealing fact about ICS SCADA is the fact that it spans automation from manufacturing to critical infrastructure. So the same factory that makes, for example, the clocks on the walls is going to be using the same basic ICS SCADA infrastructure that a nuclear power plant is going to use. And that's why we peak nuclear meltdowns. So why do I care? Every day that we have interaction with our critical infrastructure. So for example, we're in the room right now, the lights are here. How does the power get here? We have power grid that supplies that. Certain buildings are heated with gas. The control of the super systems. Anything that has some sort of automated process to it is controlled generally by an ICS SCADA system. And the big revealing one obviously is nuclear power plants. So when we look at what these systems control, we're looking at quite a breadth of things that we rely on day to day that run our country. Is really the core, the supporting infrastructure of our country that we've built over generations. So SCADA is supervisory control and data acquisition. And basically what I did is I broke it into 2 pieces to have a better understanding. Supervisory control is essentially the control that the SCADA system has over the various devices in its network. So for example, if we're talking about a water treatment plant, the water runs through pipes, you want various functions to happen to move chemicals for treatment into one portion of the facility and then move more water into it as necessary to get the right balance of treated water. So obviously, most everyone knows that water that comes out of tap has been treated, it's been filtered, and I believe it is a small amount of fluoride in it as well. Clean teeth. But these switches and valves that control that infrastructure are controlled by the ICS SCADA framework. And so the supervisory control of SCADA essentially controls those devices. It has a human interface where you can essentially go into a machine, open up pipes, open up valves, and that sort of information. Data acquisition is the other piece. So we talk to the devices and they talk back. And this is critical because when we're talking about systems that have thresholds, this is where things start to get a little bit interesting. So for example, a nuclear reactor cannot go over a certain temperature. There's a threshold there. The data acquisition piece of SCADA reports back, hey, things are getting a little warm. What should I do? Generally, it's automated, cool down the system. Water pressure in the tank, for example, electrical load on the line. Electrical load is a very interesting topic. You could really go on for days about how sending a pulse of electricity down the line will really make your day bad in a hurry. And of course, temperature in a nuclear reactor, but there are a lot of fail-safes for that one. So here comes something to blow your mind, sample SCADA output. So this is a human interface, a human-machine interface, also known as HMI. And essentially, this is the control panel that a particular user, a SCADA user, would use to control the flow. One thing to note as well, in SCADA systems, and this can seem spectacularly counterintuitive, most SCADA systems, red means open, i.e. there's water flowing. If it's green, it's blocked. So that is fantastic for yet a new user who just said, oh, all these things are closed, it's open. So that's kind of what we're looking at in terms of the interface. So what I wanted to do is deep dive a little bit into the SCADA components, so to understand the system and how these particular devices communicate. You need a little bit of information about the devices, and some of this can be a little dry because, let's face it, I don't even understand it. So remote terminal uses, these are also known as remote telemetry units. These are the units that are going to be reporting information from the various inputs in the SCADA system. So when we're talking about pressure in a tank, the RTU is going to be reporting, hey, we're at 300 PSI, we're at 300 PSI, we're at 300 PSI, we're at 300 PSI. And it blasts information out, it's steady, 1 second, maybe 5 seconds. It's constantly communicating. The reason for that, obviously, is that you want to know how much pressure is in your tank. If your SCADA system is not reporting that information, or your RTU is faulty, that's something you need to know, and generally will cause a fail-safe failover. So, additionally, it receives input from other devices, PLCs and IEDs, which we'll get into now. So a programmable logic controller. Programmable logic controller reports to an RTU. An RTU collects information from, these are the actual devices connected to the system where an RTU kind of controls it. The PLCs are basically developed as replacement for relay ladder controllers. And for those who are into programming languages, this is essentially ladder logic. When we talk about ladder logic, and unfortunately there's not many slides barring going into an hour-long discussion on it. Essentially, you set a requirement, a condition that needs to be met. If it meets it, it goes down to the next rung on the ladder and it keeps meeting the conditions. If one of the rungs of the ladder fails, it sends an alert. So it's essentially several conditional statements stacked on top of each other. So this is, as it mentions down the bottom there, this is where the rubber meets the road. The PLCs are the item on the ground that provides this information. Their failure can have a little bit of cascading results. And are really the target of when we want to hack the system.
Are those slave to the RTU, or is the RTU?
The RTU is the master, and the PLCs are the slave. So another component, this is an intelligent electronic device. So these are where IEDs can replace RTUs. So essentially, IEDs are a more intelligent unit for controlling the system. And I'll get to a master schematic. You see it all falls together. But they perform the same functions as legacy equipment, but they got a lot more features. So they'll communicate with more modern protocols, which is important, as you'll see here in a bit. And then we have the human-machine interface. Unfortunately, I got another slide on this one. As I showed you before, the human-machine interface is where the controller, this is the software that's on the controller's computer. So essentially, this is where he sees alerts that pop up and various other items that he may need to work on. Underlying all of this is the simple fact, however, that these pipes, these valves, these switches, the ISS SCADA system is controlling, all have manual failures. So literally, an engineer can go out there, pull the lever, and be safe. So worst case scenario, end of the world, if someone were to compromise the system and start wreaking havoc, if you had someone on the ground who pulled the lever, that will automatically override everything that the system will do. And so now here we put it all together. So as mentioned before, RTU controls IEDs, PLCs as well. I got cut off the bottom. And PLCs can also communicate And one of the big things to note here is the separation between the corporate local area network via firewall to the SCADA network. And that becomes important when we start talking about how we access SCADA networks from exterior networks. Additional note, wireless communications is becoming a pretty significant deal in critical infrastructure. So for example, when you're driving down the street, probably not at night, during the daytime, you see the power lines. Look at them, look at the power lines. Periodically, I think it's every 5 or so lines, you will see an antenna jumping out that's reporting information wirelessly. A lot of people don't realize that your smart grid is talking back. And one of, obviously, a concern here is the vulnerability of being able to access those wireless points and gather information.
Those proprietary protocols, or is it just WPA2?
Yeah, it converts it over to another protocol, which we'll go into later. So here, oh man, I missed this one. Here's the problem we have. Everyone here who's been in information security for any length of time is familiar with the defense in depth policy of many layers of defense to protect your critical information, the orange disk there, your data. You have your exterior boundaries, firewalls, DMZs, encryption embedded throughout. So you have many layers to protect your information. And for standard information security systems, your typical data networks, this is not a big deal. It is for SCADA, because they have one layer, and that is authenticated, and that's it, you're done. There's no power user, there's no basic user, there's no other admin. It's just when you log into the SCADA network, you're admin, and you have access to everything. There's implicit trust across all the devices on a SCADA network. So once you've logged into a SCADA network and you're communicating from an RTU to any PLC within that same SCADA network, you're golden. So once you crack the key to the kingdom, you can run around screaming your head off and nobody will care. And so that's really the big crux of the issue with SCADA security. So why do we have this implicit trust? So way back yonder in olden times, before I was born, there was mainframes, and things were wonderful because relative to security. I mean, unless someone broke in, knew the password, log in, your information was on the mainframe. One user could use it at a time. And that's what SCADA was birthed from. Essentially, the concept was when you are at the facility, such as you go to a power plant or a water treatment facility, it's a closed network. They didn't have a connection to the corporate network. It was closed. So you had one access point, and you were good to go. So why not just have implicit trust? So the other part of the implicit trust kind of bears into the fact that SCADA is very simple in design because, when we're talking about critical infrastructure, we talk about, well, let me back up. We talk about the CIA triad, confidentiality, integrity, availability. And usually, for most organizations, it's in that order. For organizations that are concerned about keeping their information safe and secret, confidentiality is top. And the integrity of the information is moved about, and at rest is critical as well. And availability, okay, if you don't have availability to it, that's fine, we'll get back later, but as long as it's safe, that's fine. It's the complete opposite for critical infrastructure. Availability is of the utmost importance, and nobody gives a rat to how much pressure is building in a particular system. Well, they should. But essentially, availability is the big name of the game, because when we're talking about critical infrastructure, we're talking about companies making money. And if we don't have power coming to our buildings, they're not making money because we're not paying them. So availability for critical infrastructure and those companies, for example, in the state of South Carolina, SCANA, SCNG, all SCANA seems to run everything in the state. That company is very, very concerned about availability. If it doesn't have availability, it's not making money. And let's face it, when your shareholders are not seeing some cash flow, people get angry pretty quick. And so for the longest time, that's all SCADA cared about. SCADA didn't care about security. So what we see for generations of SCADA, however, it's changed. Times are changing alongside SCADA. So we had a monolithic generation of SCADA where it was direct communications of devices from one terminal. That required, a human at multiple terminals, so you had to hire additional staff. But as the technology advanced, we got distributed SCADA networks, networking SCADA networks, and now we have cloud networks, and that should raise some pretty big alarms because in order to have cloud networks, you probably got to talk through the cloud. So we have a big concern there with SCADA information leaving the system and being available on open networks, and I'll get to that a little later as well. So basically, while SCADA technology is advanced, and they have done a little better with security, but not a lot, the protocols have essentially remained the same. And as I mentioned before, the only major security mechanism to get into a SCADA network is just that of basic authentication. So once you break through that one firewall, or whatever it takes to get to the SCADA network, you don't have to try and compromise an Active Directory system to get a user account and escalate that privilege. You're just in, and you can walk around and check out everything and break stuff, cause nuclear dams to flow, or sorry, cause dams to overflow. So it can be a mess. So when we talk about SCADA vulnerabilities, it haven't rammed in head enough. One of the other big items is the lack of immediate physical access to devices. So we're talking about your power grid. For example, SCADA has many different facilities throughout the state. We visited their primary facility for running their operations, where they print your bills. I found where everyone's bills print, so now I know where to go. And they have facilities where they have substations for power. They control the gas, so they have stations where gas is compressed, so it can go into long distance transport as a liquid. And so what we have here is basically you have miles and miles and miles of infrastructure. It's massive. You can't really have physical access to many devices. As I mentioned before, if you want to stop a hacker, you just pull the switch and turn it off. You'll make a large portion of the population angry. However, you won't have someone running them up through your system, destroying things. It's sensitive to many network pen test tools. So if you really want to ruin an engineer's day, break into a SCADA network and run any sort of ping suite. Really, I think Nmap will absolutely annihilate a SCADA network. The problem is that they have one focused goal in mind, that's communicate back to the RQ, and it has to do all those ancillary items. It'll start messing up the protocol, and what will generally happen is all these devices that support actual core components, valves, switches, items like that, will fail over. And it's usually a cascading effect. So if you run Nmap in a SCADA network, just about every single device is going to fail safe. Probably shouldn't. But it's a scary thing, and it's real. I mean, these things can happen. We'll go to a couple examples later on. I'll jump to the last one there, the cascading failure directed. When you lose power in a substation and you have a switch fail over, generally it sends pulse current down the line as well. As I mentioned before, current in an electrical system has to remain at a very tight threshold. Otherwise, switches are going to pop. And so if you pop one switch at a substation, if one substation goes down, it can have cascading effects. For those who remember, it was 2003 when the northeastern seaboard generator went black. It went out completely. All of the substations, I believe it started in Ohio, worked its way over to New York, and then up towards Maine, failed over even into Canada, because yes, once again, we're tied into other countries' systems as well. So their security concerns are now our security concerns, because their infrastructure affects ours. But long story short, this is a direct result of that cascading effect. The substation in Ohio, to my knowledge, it was not a hack, it was just a failed substation. Failed over, connected to another line over in Pennsylvania, and then went off from there on the high power lines. So the remote access by vendors, like many systems, vendors like to have sometimes access to your systems to provide updates. This is also true for SCADA. The difference here is that they don't have to securely log to your network. They can just go in through back doors. There's backdoors built in just about every single SCADA component for vendor access. And when I say vendors, the biggest vendor in a lot of this, I think Mattel does some stuff. The biggest one, however, is Siemens. Siemens systems are throughout the entire world. PLCs, RTUs, IVDs, HMIs. They really have a lockdown of business. I want to say it's about 70 to 80%. So if you're looking to get in the business, that's the company to talk to. Okay, so when we talk about SCADA protocols, there's really two big ones we want to talk about. This is a list of major SCADA protocols. And I want to talk more about Modbus and DMP, and most specifically about Modbus. Modbus is the biggest protocol that's utilized by many of these SCADA systems. As you see, it uses port 502, so one of the big things to look for when you're searching for a SCADA network is communications over that port. So let's deep dive a little bit into some of the famous ICS hacks. Everyone here should probably know about Stuxnet. If you don't, you really need to look into it. It's really an amazing story about how other countries interact with each other these days. So Stuxnet was essentially a focused attack on a specific industrial control system. Specifically, they were targeting Siemens systems, and a very particular type of Siemens system that happened to be used by the Iranian Nuclear Authority. What a coincidence. It used 4 zero-day vulnerabilities and compromised machines. So on the open market today, I believe organizations, malicious or good, are generally paying about $250,000 for one zero-day vulnerability. They're very hard to define and prove and exploit as well. This one had 4, which is indicative that perhaps the organization that conducted the attack had some resources and intelligence in order to do this. It was a very complex virus. It was able to jump across multiple platforms and actively seek out Siemens systems and ICS SCADA networks. Once an identified system was found, in this particular Siemens system modulated rotational speeds of centrifuges. And when we use centrifuges for making nuclear bombs or nuclear reactors of any sort, really. And so, as I mentioned before, modulation in industrial control system networks is a bad thing. Generally, I believe it was 6,000 RPMs that the centrifuges were spinning. This modulation within the time span of about 1 or 2 seconds, I believe it was 1 second, dropped it down to 2,000 RPMs, and then back up to back over 7,000 RPMs. So it did a quick drop and then punch back up, which for a centrifuge threw it off kilter and then destroyed the centrifuge. Coincidentally enough, this was a great concern to one particular country, one at the top. So this is the infection percentage of Stuxnet. And when we talk about targeting a specific country, what this generally says to me, however, is that in addition to targeting the systems, it was probably seeking out specific IP addresses. If you look at the IP range, those are going to be in the Asia IP range, I believe. So yeah, Iran, Indonesia, Azerbaijan, neighboring countries in that region were affected by it. We were not immune. We had just under 1%, not quite as bad as Iran, but theirs, of course, was specifically targeted towards their system. Now, if your system was affected by Stuxnet, your standard Windows 7, Windows XP system, then you really didn't care. It was really targeting specifically those systems that were running these centrifuges. So down to the point where it was actively looking for serial numbers, which is indicative of intelligence.
So those numbers there are the detection of the virus on the Windows platform, not in the industrial system.
I believe that's correct. That's on the Windows platform because we wouldn't be able to see the industrial system because we've gone that.
So Stuxnet was propagated by Windows networks. It was primarily focused at a closed network that was supposed to be air-gapped. It was transferred from one USB device to another USB device and things like these. The problem that comes in is that it was very, very specific in what it was looking for. When it attacked, it was looking for one thing. While it was targeting Iran specifically, the code, the one thing that we can ascertain from that is if it had gotten even in widespread in the United States, it would have done nothing. It would have just basically died on finding the code that was specific about it, tied in specifically to that in that specific region. So it's theorized that the injection point has happened over a period of time and spread throughout, and then eventually got to where it needed to go and spread pretty heavily.
And the big thing about Stuxnet too is that it's still out there. It hasn't been completely eradicated. It's on many systems, but some organizations probably just don't care to get rid of it because unless you have ICS, it's really not affecting you too badly. So Dooku is a derivative of Stuxnet, and it's less sure where this particular virus came from. It has very, very similar code to Stuxnet. It's believed to have been derived directly from it. However, it's less discriminatory in its targeting. It just goes after everything that has an ICS signature. And at the time being, right now, it's purely informational gathering. So what happens is, as it infects ICS systems, it gathers the information of the ICS system, kind of maps the network as best it can, sends information back to the command and control unit, and that's how it's collecting information right now. But because it's based on Stuxnet, it has a capability to add tools to it in the future. So compromised systems are still a concern because later on exploits can be sent down the pipe and exploited. And the big concern here is that if they've been collecting for years and years and years, this could be a large-scale attack. They could attack all of our nuclear power plants at once. They could attack all of our water systems at once, or any system that has an ICS attached to it. And I swear, if they shut down the tool plant one more time, I'll probably start with it. So, SCADA hack example. So this is another hack demonstrated, I believe, the Department of Homeland Security did this particular attack on itself, just to demonstrate the capabilities. And this tool is called Aurora. And essentially what Aurora does is damages rotating electrical equipment by one or more torque shocks. That a little later here. So how Aurora works. So essentially generators, a little background on generators. Generator that you have out at your house for when the power goes out, it's just a common commercial generator. Just a common residential generator, but a commercial large-scale generator is not something that can be easily turned on or off. Generally, it's a system that has to be stepped up very slowly and stepped down very slowly because we're talking about a generator that's connected already to an existing electrical network. So when you throw these generators out of balance, they can essentially self-destruct. And that's how Aurora works. So you have an existing network here. You got a generator on this far end, somewhere maybe in North Carolina even. You got a generator here in our state, the green one. And then you have this remote breaker that's within the transmission network. And essentially you open the breaker, Aurora executes this, opening the breaker and then closing it back into the power system out of phase. So electricity has its phases, and generally the generators have to sync up with that phase, or else the generator is going to try and catch up with it and modulate its revolutions per minute in order to do so. So by closing the generator out of phase, what we see is a break in oscillography. I think I said that right. In red is the generator voltage, in green is the grid voltage. So essentially, you open up the breaker, and for literally just milliseconds, 13 milliseconds, you have that breaker open, and you can see the havoc it wreaks on the phase right here. So you can see the red, the generator voltage shows a significant dip. The grid voltage also fluctuated, and that would be an indicator of something like that happening. And the issue with this is that as you fluctuate that, as I mentioned before, the generator is going to basically have some pretty significant issues. Hopefully this will work. Is it spinning?
White noise.
Yeah. Okay, let's see if we can move this over here. There we go, YouTube. There we go, we're on YouTube. So what you're seeing here is a generator, and they're going to spin the power spike down. You'll see it. There it was. We'll see another one here shortly. A little bit more pronounced. And eventually, if you continue to do this repetitively, and we're just talking about fluctuations of maybe 100, 200 RPMs, you're going to start having a pretty significant impact on the system. As you see, the smoke is not part of the generator. That usually doesn't happen. That's even worse. Bad things are happening. And that was a $1 billion generator.
Looks broken.
That was your government.
This is not me to do broken.
Yeah. And so we're just talking, so now the big demonstration here is that we've been able to take essentially something that should be in the digital domain and put it into the real world. This, I mean, you can have a significant impact on people's lives with this information.
Back in Arizona in the late 60s, Arizona Public Service, they brought a generator online. They didn't have out of phase when it came online, it came completely off nuts.
That would do it. And the other big part of this too is that system, because the breakers close and electricity is transmitted between the generator and the grid, you now have an impact on the grid. So after that generator fails, you probably sent some pretty bad stuff down the line in terms of fluctuation. So you're gonna be tripping breakers left and right. So you burned out a generator, your power's not coming back on for a little while, just a heads up. And you've thrown breakers across the state. So let's get into hacking. Was anybody here for Gabe's speech last presentation? Excellent. So Gabe LeBlanc is one of Spaywar's prolific hackers, and he probably gave you a pretty good introduction to some of the information about hacking. So the nice thing about SCADA, which is great, is that you can use standard hacking tools. Fantastic. So how do we find SCADA networks? So typically, some of the more popular tools in training would be Shodan. I did a simple Shodan search. Don't worry, it wasn't on our corporate network. And revealed various amounts of services from Korea Telecom, LG Powercom. So we were able to find some information. Tokyo, a little bit out of the Netherlands. Further down, there was Taiwan, and also one from China.
So I should say login incorrect. Is it trying to log in?
Probably. It might be making an attempt as well to log in.
No.
So those are the flashing lights at your house?
This is the flashing lights of the house. Yeah. The police are outside waiting for me. Everyone here generally has a good idea of Nessus. Nessus is just your basic vulnerability scanner. So now we found this out in Shodan. Let's run a Nessus scan against it. And Nessus will also reveal vulnerabilities for SCADA networks as well, because some of the SCADA networks are generally using modern protocols as well. So the big thing about finding these networks is that you generally have to still break through a firewall. And so whatever tools that you specifically prefer to use to break the firewall, usually it's a manual method to break through a firewall. But it can be done. I've seen it done. That's the things you want to find. And best of all, it uses Metasploit. You can use Metasploit to hack ICS-SCADA networks, and of course, email spear phishing. Naturally, the best way to break into networks is just get the information for free by calling them and finding out whatever you can. Social engineering remains the funnest and most effective way to break networks. But you can use Metasploit. And one interesting thing about this graphic, as I dug around for it, is as you can see at the top of that Metasploit graphic, it's on an iOS device. So someone's iPhone. So once you find the site, you can use Metasploit to access it and essentially wreak the havoc. And really, once you're in, it's once again as simple as rummaging around, mapping the network, and finding this information. But once again, quick note about mapping the network. So Nmap is going to break the network, most likely. Unless you run it extremely quietly, but even at that point, it's going to take a while to get the information you want. One of the effective ways to scan a SCADA network is to literally map it out, either by hand or a self-developed tool. There are tools out there that exist. I know one of the organizations we work with created one called Grass Marlin. But essentially, the way that you gather information is you listen. You do a TCP dump or some sort of anything else. For example, Wireshark will give you information as well. I believe the tool used Wireshark. It pulls in the communications, and based on the communications that it pulls in, not actively pinging the devices, but just listening to the lines, it's able to map the network. So, okay, so this particular IP is communicating over here, okay, this one's communicating over here. It's sending these communications, and then it's also able to give you a good idea of what system it is. So, for example, Siemens systems have unique communications using the Modbus protocol. Other vendors have their specific communications fingerprints. So once you're able to determine what organization is, what information is sending this protocol, you're also able to kind of figure out, hey, that's probably a PLC, that's probably an IED, made by this company, it's got this level of patch on it probably, and now we have a good idea of how the network's mapped out. And that's where things get dangerous.
How often does anybody think that this stuff has changed out? The average stuff in the telecom industry is over 25 years old. They very rarely get replaced. Most of them are communicating on XOR on 98 baud back to their host, and that's how they communicate. So when you slam something with Nmap with a sync scan, you're going to crush it. And you're going to shut it down.
Yes, question back.
So if you can knock these networks over with an Nmap force scan, why didn't Dooku knock them over accidentally?
To be honest, Dooku is going to, first of all, the big thing with Dooku is that it's very quiet. So as I mentioned before, Stuxnet was what Dooku was based on. Stuxnet, developed by a third party, or a pretty significant organization, probably state actor, is very quiet. It creeps around, it does very low scanning. You can scan an ICS gated network. There's some inherent risk, but if you do it less verbosely than most scanners do, then you can get away with it. Stuxnet was a long game sort of virus. It was not something that was going to pop boxes overnight. It had been out there for a while. It had been gathering information, and there was probably some command and control module that was that it needed to communicate with in order to actually execute the actual attack. So that's the big reason why Stuxnet and Dooku do not have that sort of impact on ICS systems.
So I guess the follow-up question would be the same for all these people that are now scanning the entire internet. Why haven't they accidentally knocked people over?
Because generally, scanners aren't going to find their way behind firewalls. While the industry is still relatively behind, they have started to recognize the fact that, wait a minute, we probably don't want people to hack our systems. And they have started putting up more defensive measures. So for example, any organization that doesn't have a firewall segregating their skated network from a corporate one is just asking for it. And really, they all have at this point.
There are mom and pop co-ops that are out there. It's just a matter of whether or not that corporate system that's accessible is also connected to that SCADA system.
The other piece that might be listening is that there's a difference in layers. There's the HMI, there's the PLC, and there's the RTU. The RTU is the most susceptible, and it's usually downstream. It's usually cable wired. Next to that RTU, think of an old circuit style switch. It's the same process. There's a cable that runs. The only difference now is they're distributing PLCs out 1, 2, and 3, and then they have them out, and then they have them connected via the corporate network or through a wireless connection point. Well, if you scan the network that RTU is on, you'll crush it, but you can scan the PLC, and it's listening on 502, and it's fine. And that's what exactly the PLC, the programming logic controller, was what was targeted by Stuxnet, and what caused the spin up of the RTU. The remote terminal units are designed to do basic functions, either return a number or flip a switch. Turn it up, turn it down, add voltage, take away voltage. So they're very simplistic. One of the ones that we played with basically had 3 lights on it. You flip a switch, you send it binary, and it flips a switch, a relay, to whether turn one light on, turn another light off, turn the other light on. Well, all we'd have to do is program it and run in a batch file and crash it. So it didn't take much. The PLC that was controlling it could take it all day with the end device key. That's the concern is that they get beyond the data historian. I don't know if we haven't covered the architecture yet, but you get beyond the data historian, past the PLC, you can get into where you can start changing things, like, for example, changing the messages on your Amber Alert signs on your drive to work to say accident ahead. What does everybody do? They start slowing down. But all I had to do was get past the PLC and hack into that wireless device that's sitting off the side of the road and tell it a new story, right? And then now I can do certain things. Those are some of the scenarios that we've played with in the last year.
See, that's right on point for my question, right? Is that I was just curious if you're going to get into the different topologies, right? Because I guess sort of your attack surfaces are going to vary, because obviously, these old school devices that are all hardwired together, you're not going directly to the endpoint. You got to get, some kind of network-enabled, landing zone, and then go from there, right? So you go a little bit into the...
So SCADA networks are, going back to the design that I showed you guys earlier, are very similar in design to the conventional network. You have communication devices that are gathering information from the PLCs on the ground, and the IEDs that are in the systems as well. So,
Yeah, and I guess it just depends. So it's like your example of the Amber Alert sign, right? I mean, you're inserted way into the SCADA architecture at that point, right? And you're using the weakness in the wireless physical data to basically insert instructions.
Not so much.
Not so It's not like that.
So, yeah, we had an exercise where we had to defend one of those environments. In the defense of that environment, it's a Windows workstation is the control of the HMI, the human machine interface. It controls what's going on. You type in a message, it does what it is. It does what you want to do on the other end. So if it's a Windows box, it's easily hackable, right? No problem. All you gotta do is get to the box. Get to the box, get control of it, get a remote terminal coming back. You can change whatever you want. If you figure out a way to get into the database, if there's a database mechanism, which this particular one that we had a database mechanism, all they go in is they do a database query, they figure out, oh yeah, okay, I know how this works. And all they do is write a query, send it data, turn around, change the message around. You know, we had the Epic hack where they took a screenshot and basically pasted our screenshot over the HMI so that you were looking at it, you were looking at the screenshot, total Ocean's 12 fun stuff, where you were looking at the screenshot of the old HMI, meanwhile the background had something else.
So this is basically what we were talking about here. So when we talk about the HMI interface, this is going to be on the SCADA PCs up there. And you see your SCADA firewall. So if you compromise those HMIs, already you have access to everything. It's going to be a trusted system through that firewall into this network. Because once again, SCADA security is like an M&M. Once we pass that arcane shell, it's all trusted. So going back to defending the SCADA network. So much like securing regular networks, you want to have those secure communication protocols. So there are enhancements available, Modbus and other protocols like DMP that allow secure communications. Now we're not talking AES, 256, but it's more secure. The problem is that as you add those different various layers, now you're introducing complexity and overhead into a SCADA network. And that's going to slow down processes. You may not be reporting on time. Switches may not close on time because you have encryption capability built in. So we have to be very careful about how we implement those. Locking down ports and external gateway security devices, basic stuff in terms of regular network security. Changing the default passwords of the devices is, you would think this would be a pretty easy thing to do, but remember, we're talking about engineers who are not necessarily focused on information security. We're talking about down on the ground, working with the systems engineers. They usually have to go to specific training for the device just to learn it. And then when they get it, they just want the default password because they have to manage millions of these things throughout the entire network. So it's critical to change those default passwords on devices. Like any organization, go ahead.
So, with the network as fractals and these devices will be fractals that aren't. I mean, is there anything like a patch cycle? Is there any concept?
Here's the hard part about patching infrastructure, because for example, when you patch a network, with Microsoft patches,
Is it even relevant with all the information?
To a certain degree, it's not, because the problem with patching these systems, you have to take them offline. And now you start getting to the business case of why are we doing this? Because when you take that system offline to patch it, one, it takes a while for a SCADA system because it doesn't have a lot of processing power generally. And two, you're losing money every second the system's off. So for example, a conventional data network, you can usually shift the load to other devices or something like that. But when you take a device off a SCADA network, one, you shut it down, and two, you also still have to shift that load. People still want electricity. So you're generally going to have to pull from other sections of the network to increase the load. So patching SCADA networks is difficult for engineers because they have to go to their corporate leadership for some business case for doing so. And unfortunately, there's still not a big mentality of, hey, we need to keep this secure.
So you said stuff uses 408. What does that mean? I mean, so it sounds like you can wreak havoc without very much effort at all, right? So unless you're trying to be super sneaky and divert attention, and with the authentication model the way it is, right? It's just you're in, trust everywhere. Yes. What would be the point of having use, like, can you explain what it meant to have an O day and an attack? How did they use an O day?
So the 0 day was explicitly to get to the ICS SCADA network. So you can't generally access the SCADA network without going through some sort of firewall.
So you're talking about going through the hard shift. The O days were to come through the hard shift. It wasn't necessarily an O day.
No, it wasn't an O day in the SCADA network because the whole thing is an O day. say that.
So,
Gotcha.
yeah, if you get to the PLC, it's pretty much wide open. There's no encryption. There's no secure communications protocol.
Okay.
It's, you find a way. The key was is
This was a vulnerability in patching, it's.
well, it wasn't necessarily
PLC level, it's relevant.
it wasn't a vulnerability. It wasn't a vulnerability patching. I'll go a little bit deeper. What they did was they did basically a no-ops slide and they put it in memory in a space of memory that couldn't be seen. So even when they wiped it, they didn't wipe it. They rebuilt the box twice and still didn't get it to come back up the way it was supposed to. They found it later in another space of memory where there shouldn't have been data at all. And that was the odd piece of it. How did it get into the system? They had to have a Siemens system to understand how the memory allocation went in order to get it in the system and then get it to bypass a space of memory that wasn't even used by the system. So it could run and then inject its controls into the system. So that was one of the techniques that it had used. And I got this information working with Mike Poore in a course a couple of weeks back. And these are one of the things that he mentioned on those pieces. And that the concern that we had the most about understanding what it is one, the equipment's so old, there is no patch cycle. There's no standard replacement cycle. They replace stuff only when it either catastrophically goes down or they tear down a neighborhood and they rebuild and they put new stuff in. But as that's, for example, all the smart grid technology that comes into your house and how they link the communication networks between the truck that drives around your house in some places and the rest of the newer smart grids are the house-to-house communication, much like we used to use in Seagar's radios where we do the network hop over the radios. They're basically using the radios to network the houses together to pass the telemetry back to the substations on what individual houses' usages are so they don't have to send a truck out there. Well, those systems, if they don't go down, they don't break, how old does a house sit? 20 years, 30